Yeah, so as introduced, my talk will be about Brauer Group and Galois cohomology. And this is a joint work with me and Addison, also from Imperial College. And the title is Brauer Group and Galois cohomology, but what we did is something simpler. So the final goal is for an arbitrary field K, we want to prove, well, that thing should be a big K. So we want to prove is the Brauer group over K is the same as the second Galois cohomology of the separable closure or separable closure of K acting on the units of separable closure. And because Galois cohomology is a bit tricky to do because it concerns topology and whatnot. So we start with a finite dimensional Galois field extension first, and we can sort of think the separable closure as the direct limit or the union of all the finite dimensional Galois field extension. So on the left-hand side, we'll be having something called the relative Brauer group of big K over small k, and on the right-hand side, we'll be having the second group homology of the Galois group of big K over small k acting on the units of big K. Yeah, we'll introduce what the relative Brauer group is and what the second group homology is if you haven't seen it. So the central object we'll be studying is something called central simple algebra. So what is a central simple algebra? Central simple algebra is basically a central algebra and a simple ring. And an algebra is said to be central if the center is exactly the field. And a ring is said to be simple if the zero and A are the only two-sided ideals. And yeah, A is central simple if it's central and simple. So central is relatively easy to define in Lean, but what about simple? So the object we're concerning is two-sided ideals. So how should we do two-sided ideals? And there are some criteria we need to consider. We don't want to repeat too much code. I mean, the easiest thing to do is to write down a structure and just like ideal and some property saying it's two-sided and reproduce all the lattice structure by hand. And another criterion we want to do is we want to define quotient rings very easily. So because the only reason we want two-sided ideals, I mean, the only reason for me to want two-sided ideals are to quotient them. So happily, we already have a ring con, which is a congruence relation on a ring which respects addition and multiplication, and ring con can be quotient in MATLAB. So we can just say a two-sided ideal is is nothing but an equivalence relation. But wait, two-sided ideals are sets. How should we do that? We need to talk about membership. Then we say, okay, two-sided ideals are sets, and R is in a two-sided ideal if and only if R and 0 are related by that congruence relation. And yeah, this works fine because, and this is in some sense quite unusual in MATLAB because in some sense all the set-like instances in MATLAB before two-sided ideals are like submodule, subspace. The things are literally sets, but now we are treating an equivalence relation as if they are sets. But luckily, we haven't run into any problems yet, but we will see, I guess. So here are some classical results concerning central simple algebras. So if K is a field and A is a finite dimensional simple K algebra, then we can classify all the simple algebras by division rings. That is for every finite dimensional simple K algebra, there will be some positive integer n and some division algebra such that A is just a matrix algebra over S over the division algebra. And we can prove that the positive number n and S are unique in the sense that if M and S prime are another pair, then n is equal to M and S is isomorphic to S prime. And some corollaries of Wedderburn-Artin theorem are, so if M is an A module, then there will be a simple there will be a simple A module S such that M is just copies of S. So yeah, so one of the corollary that is harder to prove is that if M is an A module, then there exists a simple A module S such that M is just a copies of S. And in fact, this simple module S is unique. And another corollary is that if M and N are two finite A module and a K module, such that the A action and the K action are compatible, then M and N are isomorphic as A module if and only if their K dimensions are the same. And the proof is just pulling back module structures and playing around with finite dimensionality, and eventually you will see that the indexing set must be the same. So M and N must be isomorphic to each other. And another classical theorem, which we use a lot when we are showing the isomorphic relation between the group cohomology, is something called Skolem-Noether theorem. This says if A and B are K algebras such that A is finite dimensional and central simple and B is simple, then any two K algebra homomorphisms from B to A only differs by a conjugation. That is, here there's a typo. Here should say, yeah, maybe I should do this. Here should be FB equals to A times G of B times A inverse. And another theorem we'll be using a lot is called double centralizer theorem, which says if A is a field, if K is a field and A is a finite dimensional central simple K algebra, and S is a simple K subalgebra, then first we know that the centralizer of S will be simple. And the second thing is we have the centralizer's dimension times the dimension of the submodule itself will be the dimension of the whole thing. And in fact, we can in some sense write we can write A as the tensor product of the centralizer and the submodule. Then finally, just by playing around with the isomorphism and dimension, we can see that the centralizer of the centralizer is itself. Yeah, so the proof is one direction is very trivial, and the other direction is because the centralizer is simple by the previous lemma, then we can use the previous lemma to have these strings of equalities in dimensions. Then finally, if we cancel out the dimension of centralizer of S, we will see that the dimension of centralizer is the dimension of S. So the centralizer of centralizer must be S itself. And now we are ready to construct Brauer group. First, we need a lemma that says if that says central simple algebras are closed under tensor product. So the first lemma is if A and B are central K algebras, then A tensor B is also central. And the proof is just that center distributes over tensor product. And the other theorem is if A is a simple K algebra and B is a central simple K algebra, then A times the A tensor B is also central simple. And the proof is a bit complicated, so I didn't include it here. So these two lemmas combined together, we will see that finite dimensional central simple algebra over K is closed under tensoring over K. Then we can start to define what the Brauer group is. First, we define the equivalence relation that we are going to be quotient. So I will use the CSA to just denote the set of all finite dimensional central simple K algebras. And it's actually not obvious why this is a set, but in fact, this is a set. So in linear, you can see that when you define this structure, if all your K and A and B are in type 0, this thing will be having type 1. That indicates that to Lean that it's not obviously a set. So it's larger than the universe the original objects are in. But in the end, we can prove that it is actually a set. Whatever it is, but I guess most of us doesn't really care about this. So yeah, so back to the main point. Two central simple algebras are equivalent, are Brauer equivalent, if there exist positive natural numbers M and N such that the M-dimensional matrix algebra over A and the N-dimensional matrix algebra over B are isomorphic as K algebras. It seems a little bit arbitrary, the equivalence relation, but there is another characterization, which is maybe a bit more natural. So A and B are Brauer equivalent if and only if their category of modules are equivalent as K-linear categories. And if we use this equivalence defined in terms of equivalence in category, then we will see that obviously this is a equivalence relation. So if we quotient by this equivalence relation, we get the Brauer group over K. So some lessons I learned from when doing this part is that maybe it's a good idea to write down the full picture first before you start doing anything, because we proved that this relationship is transitive by using the matrix definition. So you just compose with 1, 2, 3, 4, 5, 6 isomorphisms together. And in Lean, you need to do a bit more because like matrix over a matrix of dimension m times n is not literally matrix of dimension n times m. So you need to compose some trivial isomorphisms. And after wait, how do I go back? And after we finished proving this is an equivalence relation, we discovered that we actually need to prove that the matrix definition is actually equivalent to the category definition. So we did that again. Then on hindsight, if we are going to prove that these two equivalence relations are the same anyway, we should just define the Brauer equivalence as the category using the category one. Then we don't have to write this ugly thing. And no, I can't go to the next slide. Okay, so we claim that it is a group. So what's the multiplication? The multiplication is just pick a representation, say it is A, and pick a representation, say it is B, then send it to A tensor B. And what is the unit? The unit is the equivalence class of K. And what is the inverse? The inverse is the opposite algebra. And we can check everything is well defined. And so it's not that hard. It's just very long. And now we can talk about base change. So if E over K is a field extension, and if A is a central simple K algebra, then we can prove that E tensor A, which we call the extension of A, is a central simple E algebra. So previously we have seen that E tensor, the extension of A is simple. So we can see that the center of the extension of A is just the center of E tensor the center of A, which is just E tensor K, which is just E. So this is central as well. Now we want to because if A is central simple over K, then the extension of A is central simple over E. We now have a set theoretical map from the central simple algebras over K to the central simple algebras over E. Now we just need to check that this map actually respects the Brauer equivalence. So let's say A is Brauer equivalent to B over K, and now we want to prove that the extension of A is Brauer equivalent to the extension of B over E. So we can assume that the matrix algebra M is the same as matrix algebra of B for M and N. Then it's a general fact that the matrix over A is the same as A tensoring matrix of the base ring. So we have the first isomorphism, and now we can expand the second isomorphism is because why is this true? Oh yeah, it's because on the right hand side, so this matrix E part is the same as this as K algebras. But now then we can actually so this isomorphism is naturally just a K algebra isomorphism, but we can prove that it is E algebra isomorphism as well, because for any element E in the field E, then its image on the left hand side here and the image on the right hand side here are the same. And now we can the third isomorphism is induced by A of E mapped to this, and E tensoring the matrix mapped to this, and we can this is injective because the domain of the homomorphism is simple, and this is surjective because we can find pre-image for this for the basis. And finally, we can use the isomorphism in the first step again to combine this into to combine A tensor the matrix into matrix ring over A. And we do the same for B. And we combine these two together, we will see that in fact they are Brauer equivalents over E. And in Lean4, all these isomorphisms are doable because we have very nice universal properties. It's just for some reason the class instance seems to be struggling a little bit. So the highest I go is this 1.6 million or 16? Yeah, I lost count. But so anyways, Lean can search this eventually. You just need to make a cup of tea and wait for it to do that. Yeah, and checking that. So we have a set theoretical map from between the Brauer groups. So we just need to check the preserves multiplication, and this is just a standard fact in commutative algebra or non-commutative algebra. So we have a base change morphism from Brauer group over K to Brauer group over E, and in fact, it's very easy to prove that this Brauer group actually is a function from the category of fields to the category of groups. So this just boils down to prove that the extension from K to K is the identity, and the extension and base change composes. So which again boils down to K tensor A is just A, and E tensor F tensor A is just E tensor K. It's tensor product absorbs. So now we're finally to define one of the main objects. The relative Brauer group is just the relative Brauer group of E over K is just the kernel of the base change map. So if we unpack the definition a little bit, we will see if A is a central simple algebra, then A such that E tensor with A is a matrix algebra over E, then A will be in the kernel. So this motivates us to have the following definition. So we say that E over K is a splitting field of a central simple algebra if E tensor A gives you a matrix algebra of E. Then we will have that E split if and only if A is in the relative Brauer group. One direction is just by definition. On the other hand, if A is in the kernel of the base change map, then by definition we will see that for some non-zero n, the matrix of dimension n over the ring E tensor A will be the matrix of dimension m over E for some m and n. And on the other hand, by Wedderman-Artin theorem, we can find some E division algebra D such that the tensor product of E tensor A is just the matrix algebra over D. Then if we enlarge all the indices to their common multiples, we will see that matrix algebra over E is the same as matrix algebra over E tensor A is the same as matrix algebra over D. So because the existence of D and the index are unique, according to Wedderman-Artin theorem, we will see that Pm is equal to P squared n and is isomorphic to D. Then finally, we will see that E tensor A is just a matrix algebra, which means E splits A. And what's this slide? Oh yeah. So if K over F is for some reason I'm arbitrarily naming these fields. So if K over F is a finite dimensional field extension, then for any x we say a central simple algebra A is a good representation of x if embeds into A and A represents x, and the F dimension of A is the square of the K dimension of F. So we call this a good representation. It is because before this x is some mysterious things that we don't know much about. But now we lost no information in the context of Brauer group if we replace x with A. But now we have a K embedding, and we have a nice formula for the dimension of A, which we can play around with. So suppose K splits A, then the aim of this lemma is to prove that then A can actually be replaced by a good representation. So the first thing we do is so if K splits A, then there exists a central simple algebra B such that A and B are inverse in the Brauer group sense, and the dimension of B is correct. And the proof is, by definition, if K splits A, then we can find K tensor A to be a matrix algebra over K. And the matrix algebra over K is an endomorphism ring, is the endomorphism ring of vectors over K. And so we can just define an F algebra map from A to the endomorphism, the F endomorphism of K to the power of n by composing this in together. Where this last thing is restricting K linear maps to F linear maps. And because A is simple, this whole composition will be injective. Therefore, the image of A and A will be isomorphic as F algebras. So now we define B to be the centralizer of the image of A in this ring, which I can't even pronounce. And now we can just construct an F algebra map from K to B by multiplying on the left hand side. And we can see that B is a central F algebra. Why? Because if X is in the center of B, we want to show that X is in F. We first show that X is in the image of A. This is because since X is in the centralizer, we show that X is in the centralizer first, and we apply the double centralizer theorem. And X is in the centralizer is because X is actually the center of B. So if you just expand everything out, you will see that this implies that X is a centralizer. And note that B itself is defined to be a centralizer here. So apply double centralizer theorem, you will see that X is actually in the image of A. And now we prove that X is in the center of the image of A. This is because if A is an element of big A, we need to check that X times the image of A is equal to the image of A times X. And this is because, again, B is the centralizer of something. So we see that X is in the center of image of A, but image of A and A are the same. So X must be enough. And what is this? Oh yeah, we proved the injective. What did we prove again? Let me see. So we proved B is central. Now we need to prove, presumably, B is simple. Yeah. So B is simple because B is a centralizer, and we see in the lemmas in a double centralizer theorem session that we only need to prove that iota is a simple ring, and iota is a simple ring just because iota is just A. So now we need to prove. So now we need to prove that they are inverses to each other, and this is because again by double centralizer theorem, we can decompose a ring into a sub algebra times tensoring with the centralizer of that sub algebra. So now we are decomposing this endomorphism ring into the sub algebra I of A with the centralizer of I of A. And this is isomorphic to A tensor ring B, and because endomorphism rings are actually just matrix rings if you choose a basis. So we see that A tensor with B is a matrix algebra over F, which by definition means that A times B is 1 in Brauer group. And now we just need to calculate dimensions. So the dimension of B times the dimension of A is equal to the dimension of B times the dimension of the image. And by double centralizer theorem, this is equal to the dimension of the endomorphism ring. And the dimension of endomorphism ring is just the dimension of K to the power of n squared. And the dimension of K to the power of n squared is something easy. And so finally we see that dimension of B times dimension of A is equal to n squared times dimension of K squared. And this gives us that dimension of A is n squared. Comparing this equation with with so comparing these two equations, we can cancel out the n squared, and we see that the dimension of the dimension of B is this part. So yeah, now we figure out how to find a good representation of the inverse of A. We just need to take that good representation and put an opposite ring on it. We get a good representation for A. So the important theorem is that K splits A if and only if there exists a good representation of A. So one direction we have already seen. Now let's say if B is an arbitrary good representation, then we can give B a K module structure by multiplication on the right. That is, if A is an element of K and B is an element of B, then we define the scalar product of A and B to be B times iota of A. And since B is a finite dimensional F vector space by the definition of good representation, and K over F is finite dimensional field extension, then B must be finite dimensional as a K vector space as well. So and we have assumed that B and A are the same in a Brauer group. So to show that K splits A, we just need to show that K splits B. And to show that, we define an F bilinear map from K to B to the endomorphism of B by taking an element of K and an element of B and send it to left multiplication map. And this descends to a linear map on the tensor product. And we can actually check that this map is K-linear as well. And you can also check that this map actually preserves multiplication. So it is in fact a K-algebra map. And this K-algebra map is injective. It's because the domain is a simple ring. And this K-algebra map is surjective because we can calculate dimensions. And yeah, it's very hard to read out. So you can just observe the equation and be convinced. So here are just some really trivial facts about the good representations. If A is a good representation, the image of the K embedding is a simple ring because it's literally K. And the centralizer of image, the centralizer of the image of the K embedding is actually equal to this image of the embedding. I'm missing an A here. This proof is somehow involved, but it more or less it boils down to double centralizer theorem. And now for any good representation, we will give it a K module structure by left multiplication. So that is for every C in K and A in A, we define the result of C multiplied by A to be we embed C into we embed the element of C into A, then we multiply them together. We can observe that if C is an element in F, and the result of treating C as an element of K, then acting on some element in a good representation, or if you let an element of F acting on the good representation directly, then the result will be the same. That means the F actions and the K actions are compatible. That means the Tower law of dimension holds, and if you have something that is K linear, then you have something that is F linear. And yeah, so and in some sense, good representations are unique because if A and B are two good representations, then A and B are isomorphic F algebras. This is because by Wedderman-Artin theorem again, we can find a common division algebra D such that A and B are matrix algebra over D. Then because of the dimension of A and B are known, then M must be equal to N, so A must be the same as B. And now we are going to learn group cohomology in 1 minute. So what is a cocycle? If G is a group and M is an abelian group, then the cocycle is a function from G to M that satisfies this equation. and you can check that all the 2 cocycles forms a subgroup. And the function from G to G to M is said to be a coboundary if there exists an x that is from G to M, so a unary function, such that such that f is equal to this. And we can also check that the coboundaries also forms a subgroup. And the second group cohomology is defined to be 2 cocycles quotient by 2 coboundaries. So if S and T are two cocycles, then they are the same in the group cohomology if and only if S times T inverse is in the coboundary. And some standard facts: if F is a two cocycle, then for any element x in G, then F1x is equal to F11, and Fx1 is equal to x acting on F11. And now we are going to slowly turning relative Brauer groups into a second cohomology group now. So now let's just assume K over F to be field extension, and we can always assume K over F to be finite dimensional Galois. Some of the theorem doesn't really require all the 2 assumptions, but just for simplicity, we will always assume K over F to be finite dimensional and Galois. So if X is in the relative Brauer group, I should write K over F here. Yeah, sorry. And then we can see that by previous lemmas, X actually has a good representation. Let's call it A. And with respect to A, we can define for every automorphism sigma, we can define a conjugation factor of sigma is a unit in A such that X times the image of C times X inverse is equal to the image of sigma C. And a conjugation sequence is just a conjugation factors indexed by every automorphism. And by Spinoza theorem, because the K embedding from K to A and the K embedding composed with any homomorphism are two algebra homomorphisms. So we can see there actually exists a conjugation sequence. Yeah, by Spinoza. And because we have defined a K-module structure on good representations, so the equation here can also be write as these two variant, and this is true because again the definition of C acting on some point is send C to A first and then do left multiplication. And if X is the conjugation factor for sigma and Y is the conjugation factor for tau, then the product of X and Y is a conjugation factor for sigma tau. So we just need to check this equation holds with by replacing X sigma with XY, and yeah, it holds basically. So what's more interesting is that if X is a conjugation sequence, then X is actually a basis for the representation. And the proof is that, let's say X is not linearly independent, and let J be a maximally linearly independent subset, then Brauer group, then we can find an arbitrary sigma that is not in J. And since J is maximally linearly independent, we see that X sigma must be we can write X sigma in terms of those X taus that are in J. And if we just restrict our attention to the J prime such that the coefficients are non-zero, we can do some manipulations for them. So the first thing we can do is because X sigma is a conjugation factor for sigma, then we know that this is true. And now we expand X sigma out. We will see that the whole equation holds. And on the other hand, if we just expand X sigma directly, we will see this equation holds. And because they are linearly independent at least, so we can see that for every tau in J prime, the coefficients are the same. So this, and because J prime is not empty, otherwise X sigma will be 0, which is not invertible, but X sigma is invertible. So that means if tau is an arbitrary element in J, then for every C in K, sigma C is equal to tau of C. That is, sigma is both not in J prime and is both in J prime. So that is a contradiction. So they must be linearly independent. And they form a basis just because of finite dimensional nullity and Galois. And now, if X and Y are two conjugation factors, then they are related by some unique C in K, such that X is equal to Y times the image of C. And the uniqueness is because everything is invertible. And the existence is because Y inverse times X is in the centralizer, and the centralizer of image is equal to the image itself. So Y inverse of X must be in K. And we denote this unique C by the symbol twist. And we can write, so X and Y are related by the fact that X is equal to Y times the image of the twist coefficient. And some properties of the twist is that if you twist X by X, then you get nothing. And if you and the twist coefficient of X and Y are invertible. So if you twist an X, so the inverse of twisting X by Y is twisting Y by X. And so we see that twist is defined by multiplying on the right. So if you want to do multiplication on the left, you need to let sigma acting on the twist. And now if X is a conjugation factor for sigma and Y is a conjugation factor for tau and Z is a conjugation factor for sigma tau, then because we have previously seen X and Y is also a conjugation factor for sigma tau, now we can define another coefficient, which we call the comparison coefficient, to be sigma applied to tau applied to the twisting coefficient of xy by z. And it has all the amazing equalities. So basically x times y will be equal to the comparison coefficient times z. And yeah, you can see all the equations here. And why do we care? This is because the comparison coefficient will be what we use to construct the two cocycles with respect to the good representation A. So the comparison coefficient amazingly satisfies this this equation, which if you squint really hard, you will see this is almost the definition of two cocycles in group cohomology. And this equation holds is because since everything is invertible and iota is injective, we just need to prove these two equalities. And because left-hand side is true by associativity, then we can just cancel this and cancel the iota. And equation 1 is true because of the combination of equations in this slide. And equation 2 is true is also because some combinations of the equations in that slide. So yeah, they are just some miracle, I guess. So by this lemma above, for any conjugation sequence X, we have a two cocycle which we denote as Z of X, defined to be this sending sigma and tau to the comparison coefficient. No, so we have a set theoretical function from not really a function, but the set theoretical thing from the relative Brauer group to the second cohomology. The plan is just to pick an arbitrary good representation A and pick an arbitrary conjugation sequence X and say that X is mapped to the to the two cocycles to the equivalence class of the two cocycles. But why is this well defined? To prove well defined, we make some observation first. Say A and B are two good representations, then A and B are isomorphic as F algebras. So let's write E as an arbitrary F algebra isomorphisms from A to B. Then by Scholar-Noether again, E composed with embedding of A and embedding of B will again differ by some U. And we have this equation just because of just because of the definition just because of the property in Scholomnosa. And another thing we care is that if A is a conjugation factor of sigma, we can push it to B by defining the push forward of X to be U times E of X times U inverse. This is a B conjugation factor. So if A is an A conjugation factor of sigma and Y is a B conjugation factor of sigma, then we can define another coefficient which we call V as the sigma of the twist coefficient of Y with respect to push out of B. Then we have then we observe that Y and the push out are related by this kind of equations. So why do we care this coefficient? It's because we are going to show that if X is a conjugation sequence of A and Y is a conjugation of sequence of B, then Z of X and Z of Y are two cohomologous. That is their division is in a coboundary. So to prove that they are in a coboundary, this boils down to prove this this relationship between the comparison coefficient and the coefficient V. And this is true because basically because how we define the conjugation factors and V. So this is true is because the definition of comparison coefficient. This is true is because how we define U. And this is true is by the previous observations, and all the following equations are the combinations, are just combinations of the equations here and here. And so if we compare this part with this part, and we cancel the U and U inverse and cancel the iota A, we see that this equation hold, and because of the definition of conjugation factor, we'll finally finish the proof. So this is so we can rephrase this lemma by saying that the two cocycle associated with Y and the two cocycle associated with X only differs by this V. That means they are two cohomologous. So to prove that they are two cohomologous, we need to prove that their division is only differs by one coboundary, and the one coboundary is literally send the row to the coefficient of X row and Y row. And so now we have a well-defined function from the relative Brauer group to the two cocycles, and it descends to a function into the second cohomology. And we can do calculation by the result of X is any arbitrary good representation and any arbitrary conjugate sequence. The result of then the result of X is just the equivalence class of that Z of X. And now we are going to do the other direction. So if K over F is a finite dimensional Galois field extension, and this Gothic A is a two cocycle, we want to construct a central simple algebra that is a good representation. So the central simple algebra we'll be using is the set of functions indexed by the Galois group. And we can see that this every element, because Galois group is finite, it's just the sum of the sequence that only has one non-zero terms. So addition is defined by pointwise, and zero is just a zero sequence. Multiplication is more interesting. So the result of multiplying the one element sequence at sigma and the one element sequence at tau is a one element sequence with this number at the sigma tau index, and one is defined to be the one element sequence with the only non-zero term a ID inverse at the ID's position. And the F action is defined by acting on the non-zero part. And this, you can check that this is an F algebra. And we can define an F algebra map from K to the cross product by sending B to the non-zero one element sequence at the ID's position with this number. And we can give again the cross product a K module structure by multiplying on the left. Then to write it out, this is just saying B times B acting on the one element sequence is by multiplying on the number. So again, the K action and F actions are compatible. And we have one lemma that says for every sigma, the one element sequence with number 1 as sigma's index is invertible. And we prove this by writing out the inverse. And another lemma is that we see the image of C acting on the left, but if we want the image of C acting on the left or on the right, then we need to change C into a sigma C. So we have this equation. Now, if you squint again, this is just saying this delta sigma 1 is a conjugation sequence, and the proof is just calculation. And again, this delta sigma 1 is a K basis, and the proof is not that hard. So I'm just going to skip it. And the corollary is because now we have a basis, we can calculate dimension, and the dimension is actually correct. So this part is more involved. Why cross product is a central F algebra? This is because if we have an arbitrary element in the center, and for any d and tau, we can multiply in this arbitrary element by this sequence on the right and get an equation, and on the left and get an equation, and we compare them by linear independence. We see that for every sigma and tau, this equation holds. And when tau is equal to ID, in particular, this equation holds. That means for all d in K and all automorphisms, if the coefficient is not 0, then sigma d must be equal to d. Equivalently, this means if sigma is not the identity, then the coefficient is 0. So this means our arbitrary element actually has a very specific form, this form. And this means because it is in the image, then Z must be in K.
We now only have 5 minutes left, and usually we
okay.
have some time for questions in the end. I mean, we can maybe extend until 5:06.
Yeah, I will be very quick. Then the next step is to prove that it is simple, and you do this by constructing a module structure on the quotient ring, and you can prove that some other thing is a basis. So that implies if I is not the top element, then they must be trivial, and so we have cross product is a finite dimensional central simple algebra. Then basically we will prove that if we have a two-core cycle, then this cross product is in the relative Brauer group, and A and B are two cohomologous. Then the cross product with respect to actually isomorphic. They are more than Brauer equivalent. They are in fact isomorphic, and this is just more calculations. And to prove that they compose to each other is actually fairly simple because as I said, if you squint really closely, you will see that they actually correspond to each other. And these are all very simple, is because not only are they cohomologous or Brauer equivalent, they are either equal or isomorphic. But in the end, the last thing you need to do is to prove that it actually preserves multiplication. This will be hard because now if you have two cocycles, then these two central simple algebras are no longer isomorphic. They are only Brauer equivalent. So you need to so the idea of the proof is you need to define a weird quotient and see in the end prove that this weird quotient is actually is actually corresponds to a matrix algebra, and finally you will see that yeah, this finally you will see, and after a lot of calculating dimensions, you will see that M is the same as some copies of simple module. Then finally you will see that finally you will see somewhere you will see that you will see yeah, finally you will see you will see the endomorphism ring over M has dimension to the fourth power, and you will finally see that the tensor product is actually this matrix algebra. So they are Brauer equivalent. And yeah, sorry, I skipped most of the proof in the later part, which are the more interesting part. But surprisingly, when I was doing this, I suspect that all the intricate calculations with sums and whatnot will be very painful and mostly manual. But I discovered when you write enough simple lemmas, they are mostly just automatic, and you just because mostly they will eventually boils down to sum of something, but the only non-zero element is on one index. So yeah, to be honest, proving once you understand the proof, that the most hard part to do in this project is actually the classical theorems, not the isomorphism itself, which I find a bit interesting. And yeah, the future works will be obviously extend this to infinite dimensional cases. And other possible way you can do the of generalizing this work is you can do. Oh, okay. So any questions? So this is the link to all the code, and if I have and very detailed math proof you can find here, and you can do it. And if you want to see how lean, what is the lean implementation, you can just click around and go to the source or whatnot. Yeah. So, and I realize I'm not sharing probably. Yeah. So again, what I just said is, what I just said is all the code you can find in this link, and in this link there is a blueprint, and in the blueprint you can find maybe I should drag this away. You can find detailed math proof, and all the math proof are linked to Lean implementation. You can click around and explore, or if you want.
What is the size of the project overall? How many lines of code?
Is there?
Oh, you can't see it directly.
Yeah, I'm not sure, but
no worries.
Maybe the percentages on the right. Like where it says lean 77%.
sorry?
On the right, where it says lean 77%.
Oh.
I've tried this.
And you can probably just guess from the file size.
Well, you read this.
Yeah, the contributors are a little bit inaccurate because I discovered most time when I push, I didn't use my GitHub account. And yeah, I don't know. It's a fairly large project. Yeah. And especially so this is Edison here. He is currently developing Azumaya algebra in some of the branches. I think it's here. He's trying to do Brauer group over general field. So yeah, and also there's a PDF version of the math proof as well. Yeah.
So if there are no further questions.
I guess I have.
Okay.
So you defined your two-sided ideals as quotients of your ring. And I was just wondering if there's like some API in MATLAB that allows you, once you've defined your two-sided ideals this way, to like describe simple rings, or like you just like have to write it out explicitly that every quotient must be either like the trivial one, like the two trivial ones.
If I understand the question correctly, is so basically, are you
like is there any, like once you've defined ideals as quotients, like is there any API in MATLAB that you can directly invoke to define simple to define simple rings, or like
you still have to define simple rings by saying the only
Yeah.
the order on the two-sided ideals is a simple order, but the good part is that the order on the two-sided ideal is almost automatic, because you can just lift the order on the quotient to your one field structure, which is called two-sided ideal. And the nice thing we use this approach is because Rincon has a very complete API. It has a complete lattice structure. So you can do span, you can do closure, you can do a intersection, you can do supremum, you can do everything, and you can just always lift this structure by using an injection.
Okay.
Yeah, so you don't need to repeat code, and you don't need to really do anything. Yeah.
Okay. Thank you.
But one thing you do need to do is you need to try to hide the fact that two-sided ideals is a ring count, because you need to either decide, like, do you want to use ring count as the normal form, or do you want to use the set as a normal form? So you need to decide that and try to hide the other thing completely.
Okay, so is your definition like irreducible or something, or like?
No, it's a one field structure. So
Okay,
if you
okay.
you need to really explicitly access the ring count field if
Yes,
you want to do that. Yeah.